Hey everyone, I'm Masood Atami and welcome to another fun dive into ML. Today we are chatting about SVM or support vector machines, a super cool algorithm that's like a genius drawing the perfect line to sort data, like separating apples from oranges. In this quick video, we'll explore how SVM nails classification with its hyperplanes and support vectors. Let's jump in. We'll start with a quick introduction to get you excited about SVM. Then we'll break down the understanding of SVM to see how it works. Next, we'll go over some key terms like hyperplanes and support vectors. Don't worry, it's simple. We'll talk about the margin, which helps SVM classify data better. We'll also explore the type of SVMs, the types of SVM like nonlinear and linear. We're gonna cover these two types perfectly. And finally, we'll touch on the drawbacks to keep it real. Let's dive in. Okay, so imagine we wanted to separate apples from oranges. SVM finds the best line, or we could say the best boundary, to distinguish between them. So, if we encounter a new fruit, it can correctly identify whether it's an apple or an orange. So, don't forget that it's a supervised learning algorithm and it is one of the most popular supervised learning algorithm and it is mainly used for classification problems in ML. You might ask me, Masood, how it works. We have initial classification that the training data is divided into two distinct groups. In this example, we have class A and class B. Then we go to model training. During the training model phase, SVM learns how to separate these two classes using the training data. Then we have a prediction. Once trained, the model is ready to analyze new data in a prediction phase. And finally, we have an output that the model determines which class the new data belong to, class A or class B. Okay, in SVM, we have positive hyperplan, the top line like a ceiling. We have negative hyperplan, the bottom line like a floor. And also we have optimal hyperplan, that is the middle line that's the best at keeping things apart. We have support vectors. These are the special data points sitting right on the edges of our lines, acting like the border bodies. We also have margin, that's the space between the top and bottom lines. And SVM tries to make this gap as big as possible so it can sort things out more confidently. So I completely covered hyperplane and support vector machine. Let's dive into margin in SVM. This is just the gap between our decision line or hyperplane and the closest data points from each group. Imagine it like a safety zone. It's found by adding the distance from the line to the nearest point in the positive group, D1, and the nearest point in the negative group, that is called D2. So the formula is simply m equal to d1 plus d2, easy peasy. Let's say, what's the big goal of the SVM algorithm? It's super cool. The goal of SVM is to draw the best line or decision boundary that splits our n-dimensional space into different groups. Think of it like a helpful guide that makes it easy to sort new data points later. And what is the best boundary? It's called the hyperplan that covered before. That is our star player. Let's talk about the types of SVM in the simplest way possible. We've got linear SVM. This is like the superhero for data that's easy to split. When we have data sets that can be neatly divided into two groups, with just a single straight line. That's where linear SVM shines. You can see it's in the diagram, those blue diamonds and green dots. SVM draws a perfect line to spread them, and guess what? The tool it uses for this job is called a linear SVM classifier. Top is nonlinear SVM. This is perfect for tricky data that a straight line can split, like these blue triangles and green circles in this diagram. It uses a nonlinear SVM classifier to sort it. Let's dive into the kernel trick. It's like SVM's secret superpower. This cool trick helps SVM tackle those tricky nonlinear relationships in data by lifting it into a higher dimensional space. Finally, let's cover the drawbacks of SVM. So we have scalability issues. For example, it's not suitable for large data sets, and we have and it requires large training time, and also its performance decreases with more feature when we increase complexity of our data sets, and it perform poorly on noisy data sets, and also it requires careful selection of kernel function. And after all, thank you for listening and thank you for your attention. I really appreciate you